I hope. All right, so that is the integral from -1 to 1, the integral from minus the square root of 1 minus x squared to the square root of 1 minus x squared. And what we're up against here is x plus x squared, right, plus xy dy dx. Notice something here. This is an odd function in y. What kind of, yep?
Sorry, this is backtracking a little bit.
Uh-oh.
Why is it the triple integral of x instead of just the triple integral?
I'm just saying let's calculate the integral of x dv. I'm not calculating the volume right now. I'm calculating the integral of x over the volume. So this is just what we're calculating. So the answer to your question is because I said so. It's not a good answer, but that's the truth. I mean, all right. So look, this is an odd function in y, right? Consequently, look, this is a symmetric interval about the origin in y. So that piece, we don't actually have to work with it. That integrates to 0. Yay! So we actually are up against the integral from -1 to 1 of x plus x squared times, well, twice the square root of 1 minus x squared, because that's what the y integral gives to us. So I'm using a trick again. What indeed, yes. So what I'm saying is I'm integrating this function, x plus x squared, over this bound. I'm doing the integral with respect to y. There is no y function here. So I'm integrating a constant over that integration region. Whenever we integrate a constant over an integration region, the answer is constant times the length of the integration region. The length of the integration region here is twice the square root, because it goes from here to minus there, which is twice the square root. That's the length of the integration region. Now, of course, you could also write down the antiderivative as y, evaluate from plus the square root to the minus the square root, and you get the same thing, right? So if you don't understand my trick, it's not the end of the world, but I'm just pointing out that this can be very labor-saving if you understand it. Oh. Ah. Ooh. Well, one thing is nice. This times that is odd. And as such, this is just the integral from -1 to 1 of 2x squared times the square root of 1 minus x squared dx, right? So that's kind of nice. And after a trig substitution, which I don't feel like, I mean, on page 287, the details are there. This ends up being pi over 4. Well, actually, do I have time to do the trig? I guess I have time to do the trig substitution. And again, the details are on page 287. It's about a half a page, this integral. What I'd rather do with the remaining time, instead of doing that, I'd like to show you another path to do this problem. All right? So I'm going to resist the urge to rehash the trig substitution here, because the truth of the matter is there is a better way. And so begins our discussion of change of variables. Because this problem is not really natural in Cartesian coordinates, is it? What would be a better choice of coordinates? What's that? Cylindrical? Yeah, probably cylindrical. We could also think of it. I mean, it depends on where you want to dive into the problem. I'm just going to talk about polar coordinate change here. We'll do cylindrical tomorrow probably. But I want to talk about polar coordinate change. And I need to kind of motivate it a little bit before I just drop the theorem on you. So let's just draw a little picture. Suppose we're in the xy plane, right? And we've got some kind of region, right? And it's some kind of, it doesn't have to be exactly like this, but it could have some kind of wiggly outside, all right? And the inside could also be wiggly, whatever. The point is that if you look at it, there's, theta 1, there's theta 2, and if I take any point in here, right? Any point in here, it's clearly between r out and this one, which would be, r in. In other words, r in, which is some function of theta, is less than or equal to r, is less than or equal to r out, which is some function of theta. These are supposed to be straight lines. Let me rescue it. There we go. All right. Anyway. So I'm trying to describe how would you integrate over this polar region. And so if we think about chopping this up, into a bunch of little sort of slices, right? Let me kind of blow it up for a second here. If we think about a typical region, we're going from, say, r over here to r plus dr, and we're going from, so this is at r and this is at theta, and then over here, theta plus d theta, right? What's the dA for this little slice? So I have r out here is r plus dr. So basically this distance is dr, right? So the d, and what's the arc length subtended then? So the dA should basically be like ds times dr, right? Where ds is this kind of distance, right? But ds is r d theta. So you see the dA, we can sort of geometrically see, it should just be something like r d theta dr, right? And that's basically it. For polar coordinates, our dA we can do in polar coordinates as r d r d theta. All right? So if I go back to this problem we were just doing, the integral of x dv over b, right? If we get to the first integral, do the first integral, what we're looking at is x squared plus y squared less than or equal to 1, right? That's what we're doing this integral over. And we had, x plus x, I'm going to multiply it out if you guys don't mind, x plus x squared plus xy, right? Do you guys agree that that problem we just did, it amounts to just calculating the integral of x plus x squared plus xy over the unit disk, all right? So the change of variables theorem, it simply says that dA is this, and we should also, when we do change of variables, we have to make the substitution for the change of variables. And what else do we have to do? We have to change the bounds as appropriate, right? So what is the unit circle in terms of polar coordinates? Well, 0 to 2 pi, right? Well, let me say 0 to 1 for r. Integral from 0 to 2 pi for my theta. Now x in polar coordinates is r cos theta. X squared is r squared cosine squared theta. Xy is r cos theta, r sine theta. You guys remember polar coordinates, right? And my dA is r. Now I got to be careful. Which one comes next? Same rules of engagement as we've been doing up to now. Theta bounds, theta differential, right? Come first, and then r comes second. But look, here, what happens when we integrate cosine theta from 0 to 2 pi? That's 0. We're integrating over a full cycle. This is 0. What happens when you integrate sine cosine over 2 pi? Again, 0, because that is 1/2 of sine of 2 theta. And that integrates to 0 because you're integrating over 2 cycles of sine of 2 theta as you integrate from 0 to pi, 2 pi. And so, look, all we have to do, see, if I hadn't got hung up on that silly volume integral earlier, I would have done the full trig substitution, so this would have, you'd have felt it more if I'd done that. So I've stolen the thunder of this example by not doing the trig substitution, but this just gives us r cubed dr, and then we've got integral from 0 to 2 pi of cosine squared, which is 1/2 of 1 plus cosine of 2 theta, d theta. But look, again, cosine of 2 theta integrates to 0 because we're doing a integral over a full period, actually 2 full periods of cosine 2 theta, right? Because its period is pi. And so lo and behold, we get 1/4 from the r integral. And this integrates to 2 pi over 2. And lo and behold, the answer is pi over 4. So I was planning to waste your time with like 20 minutes of trig substitution today. That was my game plan. But you guys asked good questions and you got me off my flow. Good job. That's good, because this was the point. This is obviously the way to do this problem, right? Because you don't feel it. But look at the notes. You'll feel it. You don't want to do this if you can avoid it. And oftentimes, making a change of variables is very, very helpful. Anyway, I shut up. Thanks, guys. Stop that.